Good morning. We're going to break up section 10.7 into two parts because it's a little bit long. And that's what we're going to do this week. Next week, I'll post a fake quiz, meaning I'll just put up a quiz that I would have given in class, but I'll also put up the solution separately. So you can take the quiz and then grade yourself and see how you would have done. All right, we're going to need to be able to do two things in order to solve today's problems. One of them is finding limits of expressions that look like this. Now in section 10.5, I showed you how to remove the absolute value of an expression similar to that, but what's different here is A, we have a limit out front, and B, there's a variable inside this expression. There's an x. Now we know n is positive, but we don't know about x. So when we remove those absolute values, which we have to do before we take the limit, we remove the absolute value from everything except the x's. So in terms of the n's, we'll end up with n plus 1 over n. All the minuses will go away. And then in terms of the absolute value of x's, we'll have absolute value of x to the n plus 1 over x to the n. Now you could do that step in your head. This is the limit as n goes to infinity. Let's write that as 1 plus 1 over n. And then simplify. Absolute value of x to the n plus 1 over x to the n is just x. So you could easily just jump from that first step to the third without doing the intermediate step. I just erring on the side of caution since you're not here with me to ask questions. All right, now we take the limit. The limit is on n, x is fixed. So the limit of this part is 1, and so we end up with 1 times the absolute value of x. So notice there's a variable in our answer. So that's going to happen frequently today. Another thing we need to be able to do is remove absolute values from inequalities. And so if I wanted to solve this inequality here, I'm going to use the rule that you see over to the right. If you have the absolute value of something less than a number, then the way to remove the absolute value is to take the expression and set it less than that number and greater than or equal to the negative of that number. All right, now you can go ahead and solve for x using typical methods of solving inequalities. We can multiply all three sections by 3. So I'm going to come up over here, running out of real estate. Negative 3 less than x minus 2 less than 3. And now finally add 2 to all three sections. So negative 1 less than x less than 5. We solve for x. All right, so now on to the topic of the day, which is power series. Power series are infinitely long polynomials. They can be centered at 0 or they can be centered at a. You can see that if you set a equal to 0 in the second expression, you get the first expression. So being centered at 0 is just a special case of being centered at a, where a is 0. Now, these infinitely long polynomials will only converge for certain values of x. We call those values of x the interval of convergence. So that's the first definition. The interval of convergence, which I abbreviate by IOC, is not the International Olympic Committee. It's IOC. That's the set of all x for which the power series converges. Typically, that set will be an interval. And the radius of convergence is half the width of that interval. So for example, if we have IOC negative 3 to 3, that means this series converges at negative 3, but it doesn't converge at 3. That's why there's a parenthesis at the 3 and a square bracket at the negative 3. So this is 3, this is 0. That's an interval of width 6. So the radius of convergence would be 3, half the width. Okay, So I have another flow chart for us in terms of how to find the interval of convergence and the radius of convergence. Now this flow chart is for a power series centered at 0, but you can generalize it to a power series centered anywhere. Now rather than go through this whole flow chart, I think it's better just to go through an example and look at the flow chart as we go. One thing I want to mention in terms of the typical IOCs you're going to see, there are three possibilities. Your interval of convergence will either be a single number where the power series is centered, and that means the series will diverge everywhere aside from that number, or the power series will converge everywhere, in which case your IOC is the whole line, or, last case, the interval of convergence will be some finite interval on the line, centered around wherever the power series is centered. A power series will always converge where it's centered, because if you look at these power series up here, so for example, if x is actually equal to a, that's where it's centered, then the whole power series just consists of this one number, c0. And so, of course, that would converge. All right, so here we go. Find IOC and R for these problems. We're going to start with summation x to the n over n times 3 to the n. So using our flow chart, first step is to use the root or ratio test to find rho. Most of the time, you're going to use ratio. So I'm going to use the ratio test, and I've already started us out. This is the n plus 1th term, and then I'm dividing by the reciprocal, well, I'm multiplying by the reciprocal of the nth term. Now the blue step you could do in your head, that's like a mental step. What I'm doing is grouping like terms so I can simplify. So in terms of what I'm going to end up with, we'll have a 1/3, because 3 to the n over 3 to the n plus 1 is a third. We'll have an n over n plus 1. That's just going to sit there, but since I'm taking a limit, I'm going to write n over n plus 1. I'm going to divide top and bottom by n, so I don't have infinity over infinity. 1 over 1 plus 1 over n. And then, again, absolute value of x to the n plus 1 over x to the n is just the absolute value of x. Okay, now I take the limit. The stuff in parentheses goes to 1. So I end up with rho equals 1/3 the absolute value of x. So let's jump to our flow chart and see what the possibilities are. We're not on this side, rho is not 0, and rho is not infinity. So we're here on the middle path. Rho is some number times the absolute value of x. So my next step is to set rho less than 1 and see what I get. Okay, so we're going to set 1/3 absolute value of x less than 1. Isolate the absolute value of x, so multiply through by 3. And now we're in the case absolute value of blah is less than some number, so this gives us -3 less than x less than 3. So I don't know the interval of convergence yet. I do know that the series converges absolutely for all the x's in this interval, but I don't know about the endpoints. So at this point, my IOC could be one of 4 things. It could be -3 to 3, including the endpoints. It could be -3 to 3, not including either endpoint. It could include the first endpoint, but not the second. Or finally, what am I missing? Not including the first endpoint, but including the second. In any of those cases, I know my radius of convergence is 3, because the width of all those intervals is 6. So I know the radius of convergence already. Now to determine which of these four possibilities I have for the IOC, I need to test the endpoints by hand. And so let's just look at our flow chart. Check the endpoints to determine if the IOC includes them or not. So the way you do that is you literally plug the endpoints into the original power series up here to see if the series converges or diverges. So when x is -3, I'm going to plug that into the original power series at the top, -3 to the n over n3 to the n. Now I want to know if that converges or diverges. Okay, I'd like to cancel those 3 to the n's, but first I need to separate the -1 to the n and the 3 to the n so that I can cancel. Okay, now we kill, and I'm left with the sum n equals 1 to infinity of -1 to the n times 1 over n. That's the alternating harmonic series. We know that converges, but I'm going to show it. I'm going to use AST, the alternating series test, with UN equal 1 over n. I hope you have your convergence tests at your side so you can take a quick glance at what they are. For the alternating series test, 3 things have to be true. 1, the limit as n goes to infinity of UN has to be 0. Check, nothing to show there. 2, the UNs have to all be positive. Check. And 3, the sequence of UNs has to be decreasing. Check, nothing to show. So that means this series converges at x equal -3. Converges, so x equal -3 is in the IOC. So that means of the 4 possibilities we had above, the ones that don't include -3 are out, because we know -3 has to be in there. So it's going to be either including 3 or not including 3. We need to check. So our next endpoint is 3. So we plug that in, again, to the original power series at the very top. So if I plug in 3, I get 3 to the n over n3 to the n. N equals 1 to infinity. This one's a little easier. I can just cancel those 3 to the n's. And this is the sum, n equals 1 to infinity of 1 over n. Okay, this diverges by the p-test. Nothing to show. So 3 is not in the IOC. So of our 4 possibilities above, the only one that works is -3 is included and +3 is not. And my radius is 3. And there is a typical power series problem. All right, moving on. So that was an example. Let's go back to our flow chart. That was an example of the middle path, which clearly requires the most amount of work. Now, the next 2 examples I'm going to do with you are the left and the right arms and see what happens there. There's much less work to do in those cases. All right, so again, we're going to start by finding rho with the ratio test. So rho is the limit as n goes to infinity, absolute value. I want the nth plus 1 term over the nth term. So n plus 1 factorial x to the n plus 1 over n factorial x to the n. Okay, limit n goes to infinity. n plus 1 factorial over n factorial. Take a guess. Hopefully you all came up with n plus 1. Again, if you don't know how to do that, just write out the top. The top is n plus 1 times n minus 1, dot, 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 down to 1. And the bottom, n factorial, is n minus 1, dot, 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 down to 1. Everything on the top cancels with everything on the bottom, except you have an n plus 1 left on the top. Okay, and then we're left with absolute value of x. Remember, you can't take the absolute value off the x. It needs to be there. Okay, now that limit is infinity unless x is 0, in which case it's 0. But for most x's, that's infinity. So let's see what to do. Now remember, for convergence using the ratio test, you need rho less than 1. Infinity is certainly not less than 1. So let's go back to our flow chart. We are here on the right branch. If rho is infinity, then the IOC is just the number where the power series is centered. In this case, it's 0. And your radius of convergence is 0 because the width of an interval that just has one point in it is 0. So back here, our IOC is the single number 0, and the radius is 0. Okay, next one. This is going to be the other extreme. We're going to find that rho is 0. I've already started us out. I took the n plus 1th term, multiplied by the reciprocal of the nth term. Everything's an absolute value. The blue step you could do in your head. I'm just combining like terms. So this is the limit as n goes to infinity. I'm going to have a 1/2. That's what this gives me. Then n minus 1 factorial over n factorial simplifies to 1 over n. So that's from this. And then I've got n plus 1 over n. I'm going to write that as 1 plus 1 over n, 2 fractions. And finally, the absolute value of x. All right, let me distribute that 1 over n in there. Limit n goes to infinity of 1/2, 1 over n plus 1 over n squared times the absolute value of x. And that limit is 0 for all x. Now 0 is always less than 1. So when rho is 0, your IOC is negative infinity to infinity, and the radius of that interval is infinity. So notice two things. When rho is infinity, the radius is 0. When rho is 0, the radius is infinity. They switch. Okay, so I'm going to end this video now and then pick up and do the second half. I suggest before you watch the second half, you actually try and do these problems. So this practice 1 is a power series that's not centered at 0, so that'll be good practice. And then I've got practice 2 and I think a practice 3. So when we come back, I'll do practice 1 and practice 2 with you and example 1. And then practice 3, I put the solutions at the end of the lecture notes. All right.